So that's how we obtain the expected value of e to the power sx from the characteristic function. And we know the characteristic function of the Gaussian to be this, it was written explicitly here, but let me just put it here, e to the power, you see, j omega mu minus omega square sigma square divided by 2. And this e to the power minus s times a appears here because I can add up the exponents. And instead of omega here and here, I just insert minus j times s. And if you arrange this, this is what you get. E to the power s times mu minus a plus s square sigma square over 2. Well, this is valid for all s greater than or equal to 0. Okay, do not forget this. This is important. Okay, if s is negative, this bound does not work. Okay, careful about that. And we would like to minimize this expression to find the tightest possible Chernoff bound. So how are we going to do that? Okay, take the derivative of this function with respect to s, equate to 0, and then, well, that will give you the extreme point. And also, let me just reiterate, keep s non-negative. This is important. Now, one trick we do here is, instead of actually differentiating this exponential function, well, since the exponential is a monotone function, you just minimize, rather than minimizing the function itself, we can just minimize the exponent, because that will lead to the same result, which is easier to differentiate. So we will just take the derivative of the exponent here, s times mu minus a plus s square sigma square over 2, which is this, equate to 0, solve for s, you get this. Okay. Therefore, plug this in this expression, okay, and then you get the Chernoff bound. Okay, probably that x, which is a Gaussian random variable with a mean of mu and variance sigma square, exceeds a, is upper bounded by this quantity here, e to the power minus a minus mu square over 2 sigma square. Now, again, I would like to reiterate, this is valid only for s greater than or equal to 0. Okay, therefore, this bound is valid only for, well, this should be non-negative because standard deviation is positive. Therefore, a should be greater than or equal to mu. Okay, and in these graphs, you see these two functions plotted for a Gaussian, well, a standard Gaussian. So we have 0 mean and the variance of 1. Since a should be greater than or equal to mu, I'm not, in fact, giving the left-hand side to the left of the mean, because the bound doesn't work there, or rather, it's not guaranteed to work there, at least. So it's irrelevant, that side. But for a exceeding the mean, this is the picture you get. So in the red line, you get the Q function, which is the actual value, and the blue line is the tightest Chernoff bound. Now you see it gets better as the function goes to the tail. This is an important observation. Okay, so Chernoff bounds, they work better when you get farther away from the mean. Okay, it's good at bounding tail probabilities. You see, it's not really very good in this region. It just gives you an upper bound, but not very tight. But after some point, it gets much tighter. In fact, this is how it looks between 4 and 5. So this is zoomed in this graph. As you see, it doesn't look very tight, but the values you get is in the order of 10 to the power minus 5. So this is what you get. Okay.